Just about everything around you was brought about by taking atoms and rearranging them to form new compounds. This process of rearranging atoms of one or more substances to form new substances is called a chemical reaction, and that's entirely what this chapter is about. Here's an example of a chemical reaction. We have ordinary zinc metal, and we're going to drop it into this flask of hydrochloric acid. We can easily see the bubbling taking place now, which is evidence of a chemical reaction. There are many different types of evidences we have for chemical reactions. We can have gas forming, as we have here, or color changes, or even solids that form. So in this video, we're going to talk about how we can express a chemical reaction in the form of an equation. So stick around. So chemists use equations to represent chemical reactions, like the one that we saw previously. This is the reaction of zinc with hydrochloric acid to form zinc chloride and hydrogen gas. In a chemical equation, we show the reactants on one side. These are the substances that we start with in this reaction. On the other side, we show the products, the new substances that arise from the reaction. We separate the reactants from the products with an arrow. You could simply think of the arrow as meaning produces or yields, as in these reactants produce these products, or these reactants yield these products. Notice that we separate reactants with a plus sign. The same goes for the products as well. Sometimes we'll even use a double arrow in some of our reactions. That is to show that the reaction can proceed in a forward direction or even in a reverse direction. In addition, we can use symbols to show the states of matter of each of the substances in our reaction. If we have a solid, we use a lowercase s in parentheses. If we have a liquid, we use a lowercase l in parentheses. If we have a gas, we use a lowercase g in parentheses. And one more symbol we'll use, AQ in parentheses. That means we have an aqueous solution. In other words, that substance is dissolved in water. In the equation for the reaction of zinc and hydrochloric acid, we see that zinc is a solid. Hydrochloric acid is dissolved in water, therefore it's aqueous. Zinc chloride dissolves in water, and so therefore this product is aqueous. And finally, the hydrogen that was released in the reaction is, of course, a gas. We can express reactions in different ways. For example, a word equation. This reaction in word equation form would read, zinc metal reacts with aqueous hydrochloric acid to produce aqueous zinc chloride and hydrogen gas. Word equations are useful for describing the chemical reactions, but it's more useful for us to use chemical formulas than words. This is actually called a skeleton equation. It gives us the basic substances that are involved in the reaction. But sometimes even a skeleton equation isn't enough. The reason is that we have to take into account the law of conservation of mass. Remember, the mass of the reactants must equal the mass of the products. Skeleton equations don't always include that information. This one is a case in which the skeleton equation is incomplete. To make it a complete chemical equation, we need to balance the equation, and that will help us correctly reflect the law of conservation of mass here. So how do we do that? It simply means we need to have the same amount of zinc on both sides, the same amount of hydrogen on both sides, and the same amount of chlorine on both sides. The way that we do that is through the use of coefficients, numbers that can be placed in front of a substance to help balance the equation. Let me show you what I mean. In this equation, we see that we have the same amount of zinc on both sides. We have one zinc over here and one zinc here. So that's good. But then when we move on to the next substance, hydrochloric acid, we see that we have one hydrogen on the left side, but two hydrogens on the right side. Recall that when hydrogen is in its elemental form, that is, not paired with anything else, it always shows up as H2. So therefore, we need to balance the amount of hydrogen we have on the left and right. We can do that by using a coefficient. Since there are two hydrogens over here, we can place a coefficient in front of this compound to balance. I want to use a coefficient equal to the multiple of what I need. Get it? So if I have two hydrogens on the right, I need two hydrogens on the left. Now you might ask the question, why can't I just put a 2 here? If I put a 2 here, I've changed the compound entirely, haven't I? It's no longer hydrochloric acid. So the only way we can change this is to put a coefficient in the front. And now in doing so, we are saying that we have 2 hydrogens on the left and 2 hydrogens on the right. Finally, we look at the chlorine. We have 2 on the right side, and now because we used the coefficient 2 in front of hydrochloric acid, we also have 2 chlorines on the left. So this gives us balance. So by using the coefficient in front of the hydrochloric acid, we have now balanced all the elements in this equation, thus fulfilling the law of conservation of mass. Let's try another example. Here we have the reaction between solid aluminum, liquid bromine, its natural state, and notice that bromine is a diatomic molecule. That will yield for us solid aluminum bromide. This would be our skeleton equation. Let's try to balance it. First, let's look at the aluminum. We see that we have 1 aluminum on the left and 1 on the right. But then when we look at the bromine, we see that we have 2 bromines on the left and 3 bromines on the right. Let's recall that when aluminum and bromide get together, aluminum has a +3 charge. It's a group 13 element. Bromide has a -1 charge. Therefore, when they arrange to form aluminum bromide, they must get together in this 1:3 ratio. So that's the reason why we have AlBr3. So the question remains, how can we balance the bromine in this case? It might help to think in terms of the least common multiple. In this case, the least common multiple of 2 and 3 is 6. So how many times will 2 go into 6? 3 times. So I'll put a 3 there. How many times will 3 go into 6? Twice, correct. So I'll put a 2 there. And now I have balance in my bromine. 3 times 2 gives me 6 bromines on the left. 2 times 3 gives me 6 bromines on the right. But now there's a small problem, isn't there? Because in placing the 2 here, I've also designated that I have 2 aluminums on this side now. How do I fix that? I simply go back and place a 2 in front of my original aluminum. And now I have balance. 2 aluminums will combine with 3 molecules of bromine to produce 2 formula units of aluminum bromide. Now let's try taking a word equation, converting it to a skeleton equation, and then balancing it to form our final chemical equation. Methane gas burns an oxygen gas to produce carbon dioxide and water vapor. Let's start by figuring out the formulas for each of these substances. Methane is given to us in the word equation, CH4. So we write CH4 and designate that it's a gas. Next we have oxygen gas. How would we write oxygen gas? Right, O2. It's a diatomic molecule. So therefore, O2, and I write a lowercase g to indicate that it's a gas. It says that those 2 reactants produce, so there's my arrow, carbon dioxide. What form is carbon dioxide usually found? It's a gas, right? Carbon dioxide, which is also a gas. And finally, water vapor. Vapor is the gaseous form of water. So I'll write H2O with a lowercase g in parentheses. This is my skeleton equation. Methane combines with oxygen gas to yield carbon dioxide and water vapor. So I've correctly represented my substances in my reaction. That was step 1. Step 2, I'm going to compare the atoms on the left side and the right side. I have 1 carbon on the left side and 1 on the right side. I have 4 hydrogens on the left side, but only 2 on the right side. And I have 2 oxygens on the left side, but 1, 2, 3 oxygens on the right side. So I've got a little bit of adjusting ahead of me. Step 3, balance the equation using coefficients. I don't have to do anything to the carbon just yet, so let me take a crack at the hydrogen. There are 4 hydrogens on the left side and 2 on the right side. How would I go about balancing my hydrogens? Right, I'll put a 2 in front of the water. Now remember, I can't change the subscripts in any way in these substances. Otherwise, I change the substance. Therefore, I must use coefficients, large numbers in front of the compound. This will give me 2 times 2, or 4 hydrogens on the right side, and 4 hydrogens on the left side. And now I have to deal with my oxygen. I have 2 oxygens on the left side, and with the 2 in carbon dioxide, as well as the 2 in my 2 water molecules, I have 4 total on the right side. Do you see that? 2 here and 2 here. 2 and 2 give me 4. So if I have 4 on the right side and 2 on the left side, how can I balance those? Right. I'll put a 2 in front of my oxygen molecule on the left side. And in doing so, now I have 4 oxygens on the left and 4 oxygens on the right. Now I have a balanced equation. The last step, we just want to check our work, making sure that we have the proper amounts of each element on the left and on the right. And we've done that. We also want to make sure we have the lowest ratio of the substances in our reaction. Let's say that I performed the balancing step, but came out with this set of coefficients. Can you see how I can factor out a 2 from each one? If you have a common factor in your coefficients, make sure you simplify them to the lowest ratio. In this case, I'll divide each of the coefficients by 2. So here again is our final balanced equation for this reaction. Okay, I've got an assignment for you. I want you to take this word equation and convert it to a balanced chemical equation. All right? So we have aqueous iron 3 chloride combining with aqueous sodium hydroxide, which produces solid iron 3 hydroxide and aqueous sodium chloride. Okay, so go through step by step, form your substances, make sure you have the reactants on the reactant side and the products on the product side, and then set about to balance your equation. You can submit your answers in the LMS. That's the end of this video. Today we talked about how to represent chemical reactions in equation form. We talked about how we can describe them as word equations, and then we moved on to skeleton equations, eventually balancing them to form our final chemical equations. We discussed the steps that are involved in forming a chemical equation, including using the law of conservation of mass to balance the equation. I hope this has been helpful to you. If I can assist you in any other way, let me know. Until next time, God bless.